Deep down, at the very foundation of modern math, there's this rule that sounds super simple. It's just about making choices. But this rule, the axiom of choice, is one of the most debated, most mind-bending ideas in all of logic. It gives mathematicians these incredible powers, but it comes at a price. A price so strange, some people just refuse to pay it. So how can a simple choice be so controversial? Let's dive in.
So, here's our roadmap. We're going to start with a classic paradox, involving socks, of all things. Then, we'll get into what the axiom actually says. We'll do a quick primer on the language of sets, just so we're all on the same page. Then, the fun part. We'll explore the totally bizarre consequences of accepting this axiom. And finally, we'll see why this whole controversy is actually necessary for math today. All right, let's kick things off with Section 1, Russell's sock drawer paradox. And yeah, the subtitle says it all. This is about an impossible choice, and it gets right to the heart of the problem. What happens when you have to choose from an infinite number of things? So, the brilliant philosopher and mathematician Bertrand Russell came up with this great analogy to explain the problem. Imagine you have an infinite number of pairs of socks, an endless sea of sock pairs. Now, your task is to pick just one sock from each pair. Sounds easy, right? Well, as Russell pointed out, there's no obvious rule you can state to make that choice. And this is where it really clicks. Let's compare socks to shoes. If you had an infinite collection of pairs of shoes, the choice is a piece of cake. You just make a rule, always pick the left shoe. Done. That rule works for every single pair forever. But with socks, there's no left or right. They're identical. You can't define a rule. So how can you be sure you can actually make that choice across infinity? You can't. Not without a special guarantee. And that guarantee is the axiom of choice. Okay, Section 2, the power of choosing. Now that we've got that sock problem rattling around in our heads, let's step away from the analogy and get into what the axiom actually says in the language of math. The key idea here is something called a choice function. Just imagine it's like a rule, or a magical hand, maybe. You give it a bunch of boxes, or sets, and its only job is to reach into every single one of those boxes and pull out exactly one item. And boom, here it is, the axiom of choice. All it says is that for any collection of non-empty sets, even our infinite collection of sock pairs where we have no rule, a choice function is guaranteed to exist. And that's the absolute heart of it. The axiom doesn't tell you how to build the function. It doesn't give you the rule. It just declares by fiat that one exists, period. Right, so here's the thing you really got to get. You only pull out this axiom when you're stuck, when you can't define a rule for choosing. If you have sets of numbers, no problem. You can just say, always pick the smallest number. That's a clear, definable rule. But for our infinite identical socks, there is no smallest sock. That's when the axiom of choice has to step in and save the day. Okay, Section 3, the language of sets. Now, before we dive into the really weird stuff that comes from this, we need to make sure we're all speaking the same language. So just a quick primer on the absolute basics, the building blocks of all this. First up, a set. Super simple, it's just a collection of things, or elements. Think of it like a bag of marbles. The order you put them in doesn't matter. A bag with a red, a blue, and a green marble is the same bag as one with a green, a red, and a blue marble. It's all about what's inside. Next up is a relation. All this does is show how things are connected. Think of it like a social network map. A relation can be messy. One person, one input, might be connected to lots of different outputs. So Adam might be connected to both Anna and Carol. Now you take that messy relation and you add one very strict rule. Every input can have only one output. Bam! You've got yourself a function. It's a clean, predictable kind of relation. If Adam is an input, he can only be connected to Anna, not Anna and Barbara. And that's why a choice function is so important. For every set you put in, it guarantees exactly one element comes out. Okay, Section 4, Paradoxes and Strange Truths. So, we did it. We accepted the axiom. We've got this guarantee that a choice function exists, even when we have no idea what it looks like. So, what now? Well, this is where things get really weird. And here's the root of all the controversy. The axiom is like a map that tells you X marks the spot, treasure is here, but the map itself is completely blank. It lets mathematicians prove that certain mathematical objects are out there, they're real, but it gives them zero instructions on how to actually build them or find them. They're like mathematical ghosts. We know they exist, but we can never see them. So, What are we talking about here? What kind of things?
Get ready for this, because this is the big one. The most famous, the most mind-bending consequence of them all. The Banach-Tarski paradox. If you accept the axiom of choice, you can prove that you can take a solid ball, break it into a handful of pieces, and then put those pieces back together to make two solid balls, each one identical to the original. Now, you can't do this with a real orange, of course. The pieces it talks about are these infinitely complex, unconstructible phantoms that the axiom says must exist. And it doesn't stop there. The axiom is what gives us those bizarre pieces from the paradox, things called non-measurable sets. It also guarantees that you can line up every single real number, pi, the square root of 2, all of them, in a single file line called a well-ordering. But it gives you absolutely no clue how that line is ordered. But it's not all weirdness for weirdness' sake. On the useful side, the axiom proves that every vector space has something called a basis, which is a fundamental tool used constantly in physics, engineering, and computer science. Okay, last section, a necessary controversy. After hearing all that bizarre stuff, you have to be asking, why on earth would anyone use this thing? Why is it still so popular? So you gotta know that most of modern math is built on this foundation, this set of basic agreed-upon rules, called Zermelo-Fraenkel's set theory. We just call it ZF for short. Think of it as the operating system for mathematics. But here's the thing. In the real world, most mathematicians don't just work in ZF. They work in ZFC. And that C? Yep, you guessed it. It stands for choice. The axiom of choice is treated like a standard plugin because despite all its weirdness, it's just too darn useful. And the history of how this all played out is just incredible. Zermelo first proposed it back in 1904. Then, decades later, the legendary Kurt Gödel proved you can't disprove it using the standard rules. Then, in the 60s, Paul Cohen proved you can't prove it either. So what's that mean? It means the axiom of choice is logically independent. It's an optional extra. You can add it to your toolkit or you can leave it out. Math will still work, just differently. It's a genuine choice. And this brings us to the ultimate choice for a mathematician. You can accept the axiom of choice. You get all this power, all these beautiful and elegant theorems, but the price is you have to accept a world filled with ghost-like objects and paradoxes. Or you can reject it. Your mathematical world is cleaner, more intuitive, but the price is steep. You lose fundamental, incredibly useful results that whole fields of science and engineering now rely on. And that's where we're left. The axiom of choice really pushes us to the edge of what our intuition can handle when it comes to infinity. It sits on this razor's edge between what we can build and see and what we can only claim must exist. And that leaves us with a pretty deep question. If a single rule can build such powerful theories, but also create impossible paradoxes, what does that really tell us about the nature of mathematical truth itself?